Hi all, Mr. Yeager here. We're looking at terminal velocity for AP Physics. We cover this because this is another equilibrium situation. Again, very much on the conceptual side, not really much mathematics involved. We don't get into major details about calculating terminal velocity, just illustrating that it's another situation where the forces acting on the object are equal during a particular motion. So what is terminal velocity? Terminal velocity is the maximum speed an object reaches during free fall. Alright? And since it's a maximum speed, that means when you reach terminal velocity, you're going a constant velocity. Which means your acceleration is equal to 0 meters per second squared at this time, and therefore you have zero net force acting on you. Okay? And so what this means is your free body diagram, we only look at the vertical, would be weight down and F of air up, and these two forces would be completely equal on you at this particular time when you hit terminal velocity. Okay? So an early question could be, what is the air resistance that you feel when you're at terminal velocity? It's just equal to your weight. So you would just do mg, and that's your air resistance as well. It's supposed to, again, make you recognize that you are in equilibrium even though you're moving very, very, very quickly, but you're not accelerating anymore. So the other thing that they might kind of look at for these types of questions is kind of like a scenario, like where you don't just look at just the ending part with the terminal velocity, but what's happening as you build up to that point. So for basically a quick little scenario, let's say basically I jump out of an airplane, have my parachute on, okay, and everything like that. Okay, I guess I can get some arms. There I am. Okay, jump out of the airplane. Again, this is before I reach terminal velocity. So it's the very beginning. This would be time equals 0, etc. What's happening at this particular point in time? So this is immediately after I jump out. My free body diagram would be weight down, and I would be accelerating at 10 meters per second squared, or g. Okay, I'd be having the full acceleration for the instant that I'm jumping out of the plane. Again, yes, there'd be some horizontal velocity and stuff like that too, but we're not interested in any of that. This is just the vertical motion down. So that's what happens at the very beginning. So you're going to start accelerating, obviously, and changing your speed very quickly, 10 meters per second per second. Well then, what happens after I have fallen for a little bit? Well, as I've fallen, okay, there's more air pushing back against me. So, as I'm falling, my weight stays exactly the same, but I'm starting to have a little bit more air resistance. So what am I doing during this time? The answer is, I'm still speeding up. But the thing is now, my acceleration is less than g, okay? That doesn't mean I'm slowing down. A lot of people misinterpret that and go, oh, you're decreasing acceleration, you're slowing down. No, I am still increasing my speed toward the ground. My velocity is still toward the ground. My acceleration is still toward the ground, but it's not changing as quickly, the velocity. Then finally, I reach terminal velocity. Eventually, I reach terminal velocity. Again, yes, there's other factors involved. I can't change my shape, okay? I'm keeping myself exactly the same shape I am the entire time during this fall. But I would eventually reach a point where I now have equal weight and air resistance. So these two things are now equal to each other, which means my acceleration is now 0 meters per second squared. But which way am I still moving? I am moving with a very large constant velocity down. So that ground is absolutely getting closer and closer and closer to me. All right? So we like to sometimes build this up. Obviously in the middle here, the air resistance is still less than the weight, okay? But I'm still accelerating. Over here, over here, you don't even know where I'm talking about. Over here where the star is, obviously right there, the idea is I haven't really started falling yet, but I'm basically about to fall very quickly. Now, it is possible that they could make you then go, okay, well, what happens when you open up your parachute? So here's some terrible drawing. Sorry, here's my parachute. Basically, it's like a thought bubble, okay? But I open up the parachute. What happens when that opens? Basically, I increase my surface area very, very quickly. We're going to see a rise in the air resistance as it hits the parachute. My weight still stays the same. My parachute was on before and after. It's just changing shape. But for a moment, the F of air will be greater than the weight, which is important because I obviously want to slow down. Okay? The thing is, I'm still going down velocity-wise, most likely. I mean, it's possible that it could reverse your direction and bring you back up for a moment. But again, we're not getting too technical with this. It's just that it would slow you down. Okay? The thing is, as you slow down, what happens is, if you're slowing down, less air is hitting the parachute. And so what happens is you actually reach a second terminal velocity with the parachute open, possibly. Again, as long as you don't mess with it or change anything. You can hit a second terminal velocity, which means, again, your weight is equal to your air resistance. So a couple questions can come out of that. Some questions can be, tell me about the air resistance during the second terminal velocity compared to the air resistance when I didn't have my parachute open. Okay? Well, would one of the air resistances be larger than the other one? Okay? During first, I'm going to just write TV, terminal velocity. All right? Is the air resistance greater now that I have the parachute when I'm at the second terminal velocity? Or is it greater or less than the first terminal velocity? The answer is these two are equal to each other. And why are they equal to each other? Because what didn't change? My weight. During this time, the F of air and weight are exactly the same. So therefore, it doesn't matter what terminal velocity you're going at. As long as you are not losing weight somehow in the middle of flight or gaining weight during the middle of flight, the air resistance should be the same in both terminal velocities. What will be different is the second terminal velocity will be less than the first terminal velocity, because the idea is you had less time. There's less time for you to basically accelerate before you reach equal air resistance and weight, less time, and therefore you're not accelerating as much, versus the first time you accelerate for a longer period of time because it's taking longer for that air to match your weight, and therefore you'll be going a higher terminal velocity the first time without the parachute versus with the parachute. So that's basically it. Again, terminal velocity is just another equilibrium situation. You're going to constant velocity. Keep that in mind when you then have to put those forces together and go, hey, these are equal forces. Think about what's happening as you're building up to terminal velocity. You are accelerating, you are getting faster, but maybe not at 10 meters per second squared, and that's about